Welcome back. This is the continuation of our System Verilog session on classes. In our first session, we have already covered what System Verilog classes are, how objects are created using constructor, what is the lifetime of the class properties and methods, and how static properties behave. Now in this session, we will be covering about inheritance, method overriding, polymorphism, encapsulation, and abstraction. So let's get started. Inheritance allows us to create new classes called derived classes that can inherit properties and methods from another class, which are called base classes. So this concept is extremely useful when we want to reuse the existing code. For example, we can take existing classes from our previous projects and can extend them or modify their behavior without rewriting everything from scratch. Now with inheritance, we can add new features such as additional data members or new methods. We can even override the existing methods to change their behavior. So with inheritance, we don't need to modify the original class. So this makes our code much more maintainable and easier to debug. So let's see an example to understand how inheritance works in System Verilog. We start with a base class named packet and it has three properties: payload, destination, and priority. Next, we define a new class called extended packet, which extends the base class packet. So extends is a keyword here, and the left hand side name is the derived class name and the right hand side name is the base class name. So extended packet is a derived class which is being derived from the packet class, means it automatically inherits all the properties and methods of the packet class. But in addition of this, it introduces two new data members, packet ID and checksum. And these are specific to this derived class. So you can see we have added more functionality in the derived class without changing the original packet class. So inheritance allows us to build on top of existing classes and it allows us to reuse the code while adding new features. Now let's understand the concept of overriding in System Verilog. When a method is defined in a base class, it can be overridden in the derived class by redefining it. Say for example, you have some function defined in the base class, and if you want to change the behavior of this function, you can do this by overriding it in the derived class. Let's understand this with the help of an example. We have a class named packet, and this is a base class, and inside this packet class we are defining a method display and we have marked it as virtual. So this virtual keyword tells the compiler that this function can be overridden. Then in the extended packet class, which is derived from the packet base class, we are overriding this display method. So while overriding, the signature of the function should exactly be same. Means the function name, return type and arguments all should be same. Now in the overridden version, we are displaying all the inherited fields, payload, destination and property, along with two additional fields, that is packet ID and checksum. So this shows that each derived class can implement its own copy of the overridden method. So let's now talk about the super keyword and System Verilog. So super keyword is used in a derived class to refer to the overridden members or methods of the parent class. So there are two common scenarios when this super keyword is used. First is to call the base class constructor using super.new. So this is helpful when you want the base class to initialize its members first. And next is to access a method or a property from the base class that has been overridden in the derived class. So let's see an example. In the earlier example of the method overriding, there is a display method in the base class, and there we are displaying its members, payload, destination, and the priority. And the same method is overridden in the derived class, and there we are displaying all the base class members as well as its additional members. So in the overridden version, instead of duplicating the code to display all the base members, we can simply call super.display. It will call the base class display version, and then we can only have code to print its additional members in the derived version, that is packet ID and checksum. So let's now walk through an example to understand how super is used in practice. So on the left hand side, we have same packet class which defines some basic properties, and it has a constructor to initialize the values for these properties and a display method to print all these properties. On the right hand side, we have a derived class named extended packet. It adds only one property here, that is packet ID. Now in the constructor of this derived class, we are using this statement super.new. So what this statement would do? This would call the base class constructor and initializes all the inherited fields from the base class. After that, we are initializing the new field, that is packet ID. In the overridden display method of the extended packet, we are first calling super.display, and then we are adding our own print line to display the packet ID. So when we are calling this super.display, it would call the base class display version, and then we are displaying its own property. So the main point here is super allows us to extend functionality without rewriting everything from scratch, and it makes our code more cleaner and more modular. So there is an important point here. Every time when child object is created, constructor of parent is called implicitly. So even if you don't explicitly call super.new inside a derived class constructor, system Verilog will do it automatically. Take this simple example. We have a parent class with a constructor that displays parent class. Then we have a child class that is extending from parent, and its constructor also prints child class. Now the child class constructor is not calling super.new. But when we are creating an object of the child class, then you can see in the output, first the parent class is getting printed and then the child class. This is happening because system Verilog implicitly inserts the super.new call in the child class constructor. So if you are not doing anything special in your constructor, you don't need to manually call super.new. It would happen by default. Now let's look at a case where we actually have to call super.new manually. So in this example, the parent class has a constructor that takes string argument, and there are no default value provided for this argument. Then we are extending this class in the child class, and we are defining its own constructor, but we forget to call super.new. Now what would happen here? When we are creating the object, then it is not implicitly calling the parent constructor. Why? Because parent constructor needs a string argument. So it would give error as super.new is not called. So base class constructor won't be called unless all of its arguments have default values or we call it explicitly with required number of arguments. So the main point here is if the parent class constructor require arguments and does not provide any default values, then you must call super.new yourself and you have to pass all the necessary values. Alright, till now we have understood the concept of inheritance, function overriding and super keyword. Now this is a small assignment for you all to try after the session. So in the first step, add a new method called calculate info in the base class packet. This method should return a string with some basic packet information. For example, you can return something like payload and its value. In the derived class extended packet, override the same function. And inside this method, first call the base class version using super and then append additional information. For example, you can append something like packet ID and its value. Finally, modify your test bench module, create object for the base class as well as for the derived class and call this newly written method for both and display the returned string using $display. So with this assignment, you can see how method overriding works, how we can reuse base functionality using super, and how both classes behave differently when the same method is called. Next topic is polymorphism, and it is a very important concept in object-oriented programming. It enables us to write code that can handle different type of objects in a generic way. In system Verilog, polymorphism allows a base class handle to point to an object of derived or child class. So this way we can access methods of the child class through a base class reference. This is a powerful feature when writing test benches in UVM. So polymorphism is mainly achieved through three key features. First is virtual functions. By declaring a function or task as virtual, we allow derived class to override its behavior. Next is method overriding, where the child class redefines the method that is already defined in the parent class. And last is dynamic method dispatch. This is what enables runtime polymorphism. It means that the decision about which version of a method to call that is made at runtime depending on the actual object type that the base handle is pointing to. So overall polymorphism helps us in writing more abstract, more reusable code and it is very heavily used in verification methodologies like UVM. So let's understand polymorphism with this simple example. Here we have a base class called shape and it defines a virtual function called display area. This function is just printing a default message indicating area is undefined. Now we are deriving a class rectangle from the shape and rectangle class also overrides the display area function and it prints the area based on width and height. We are again deriving a class triangle from the base class shape and it is also overriding the method display area. On the right hand side, we are declaring a base class handle and the derived class handles. Now initially in the initial block, we call shape.display area. So it would call the display area function from the shape class, that is this one. Then we assign shape equals to rectangle. Now when we call shape.display area, it would call the rectangular version of the function. And later when we assign shape equals to try, the same function would now invoke triangular version of the display area. So this is dynamic method dispatch, means decision of which method to call that is made at runtime based on the object that this base class handle is pointing to. So here base class handle is pointing to rectangular object. So it would call the rectangular version. And here base class handle is pointing to triangle object. So here the triangle version of display area would be invoked. And this is what polymorphism in system Verilog. So here we have some important points about polymorphism in system Verilog. Firstly, in object-oriented programming, you can assign a derived class object to a base class handle, but the reverse is not allowed. So as shown in the code snippet, shape is equal to rectangle. This is valid because we are assigning a derived class object to a base class handle. And shape.display area, it would call the rectangular version of the method. Next, shape equals to try, it would call the triangular version of the display area method. Next, we are assigning a base class object to a derived class handle. So this is not allowed and it would throw an error. Now let's talk about the role of virtual. If we do not make our function virtual, then method to be called is resolved at compile time. Means the base class method would always be used irrespective of which object we have assigned to the base class handle. But if we make the function as virtual in our base class, then the method lookup is delayed until runtime. And the version of the method that is called, that is based on the actual object type that is assigned to the base class handle. And that this is what enables polymorphism. So since we have understood how polymorphism works, so this is a simple assignment to practice the concept. First, start by enhancing your packet class by adding a virtual method called getPacketType and return a string from this method, say base packet. Then override the same method in the extended packet class and return the string, say extended packet. Now modify your test bench module and create objects for both the base class and a derived class. Use a base class handle to call this method and observe how the correct method gets called depending on the actual object. Next, you may also create a new derived class, say priority packet, which is extending from the extend packet class, and override the method here also and test polymorphism. If you do all these assignments yourself, you will definitely get better understanding of method overriding and how base class handles can be used for extendable code without touching the original base class. So the next important topic is parameterized classes. So in system Verilog, just like modules can be parameterized, classes can also be customized using parameters. And this makes our class definition more flexible and reusable. For example, with this packet class, we have 4 parameters: payload width, destination width, priority width, and we have a type parameter called data type. So inside this class, we are using these parameters to define data members like payload, destination, and priority with customizable widths and type. Now see how we can instantiate these classes. So with the first instantiation, we are using the default values which we have passed, which we have set here. For other instantiation, I am passing the overridden values. For example, with, with packet 2, I am passing 16-bit for payload width, 64-bit for destination width, 3 for priority, and logic uses logic as the data type. Packet 3 is overriding only the bit data type as a 4-bit bit vector, and for others it is using the default values. Packet 4 is setting payload and destination width to 16 and 128, and it leaves others as default. So the main advantage of parameterized classes is that you can avoid code duplication. since same class can be used across multiple configurations. So let's move on to the concept of encapsulation, which is very important in object-oriented programming. So encapsulation is all about bundling the data and the methods into a single unit, which is the class itself. It also includes restricting direct access to some of the class component. So encapsulation keeps both the data and function safe from outside interference, and it is also known as data hiding. So how can we achieve encapsulation? So it is achieved using access specifiers, which are the keywords that define the level of access to class members. So first is public, and it is default access specifier. And if any member or any method is public, then those members are accessible from anywhere, from inside the class or from outside the class. Next is protected. If any member is protected, then these are accessible within the class and also by any classes that is derived from it. And the last is private or local. So these members are only accessible within the class itself. They cannot be accessed by the derived class, or they cannot be accessed by the outside world. So usually we make properties, we declare properties as private or protected to prevent external code from accessing or modifying it directly. And we declare our methods as public, and they can access these private properties. So it gives us control over how data is used. Let's look at an example to understand how encapsulation works in System Verilog. On the left hand side, we have a class named packet. It contains a private property called payload, and it's an 8-bit signal. Since this property is private, we cannot access it directly from outside the class. So we are creating two methods, a getter and a setter method to interact with this property. So the get payload function returns the current value of the payload, and the set payload is used to modify the payload by passing a new value to it. Now in the test bench module, we are first creating a packet object named P1 and initializing it with a value. Using the get payload, we are getting the payload value and we are printing it using the $payload. Then we are updating the payload value using set payload method. And finally, just to demonstrate this, we are trying to access the payload directly using this object, but it would result in a compile time error since this payload is private property. So this is how encapsulation helps in direct access of the private data. So this is an assignment to help you practice encapsulation in System Verilog. So first add a new private property to the packet class and name it checksum. Next, add a method to calculate the checksum. Make sure this method is automatically triggered whenever either the payload or the destination is modified. Then implement getter and setter methods for the checksum. And finally, update the test bench module to test both the new getter and setter methods for the checksum. So this exercise will help you in having good understanding of the data hiding and access control. Now look at abstraction. Abstraction means hiding the complex internal details of a class and exposing only what is necessary to the outside world. So here the focus is on what an object does rather than how it does it. So System Verilog offers multiple ways to achieve abstraction. Say for example encapsulation. In encapsulation we make properties private or protected and hide the internal data and expose it only through controlled interfaces like getter and setter methods. So we are abstracting our properties by making them private or protected. Next, parameterization. It allows classes to be reused across different configuration by just changing the parameters like data width. And we don't need to touch the internal logic. Next, virtual method. Virtual method also helps in abstraction. How? Because it enables polymorphism and the same method call behaves differently depending on the object that invokes it. Next, interfaces. They also help in abstraction, abstracting the module communication by defining signals and hiding the underlying wiring or logic, and thus promotes modularity and clear test benches. So this is our next assignment and it focuses on implementing a singleton class in system Verilog. Singleton class ensures that only one instance of the class exists throughout the simulation. So for its implementation, make sure to demonstrate these OOPS concepts. First is encapsulation. So how can we achieve encapsulation? For this, make instance variable private and restrict direct access from outside. Abstraction. For abstraction, expose only what is necessary, like a method, and do not expose other details. Next, static properties and methods. You can use a static variable here to hold the single instance and a static method to access it. Next is access controls. You can make your constructor private or protected so that constructor won't be called from outside world and external instantiation won't be possible. Next is object sharing. So in this case, return the same object reference every time it is requested. You can write the test bench module and try to get multiple instances and verify that all of them are pointing to the same object. Please feel free to connect with me over mentioned email ID or follow me on LinkedIn to get more updates. Thank you.